Year 13. In this weekly review, we're going to look at the efficiency of the bubble sort and the insertion sort algorithms, and then look at some of your homework solutions. Right, again, if we just revise it, both these algorithms are what we call n-squared algorithms. You will see that there is an outer and an inner loop in both. So at worst case scenario, it's going to be n squared. If we've got 10 elements in an array, there's going to be 10 outer passes, 10 inner passes, therefore 100 operations to sort the array. We're going to look slightly, a wee bit more in detail when maybe the insertion sort is a better option than a bubble sort, even though they're both classified as n squared in their efficiency. So if we begin by looking at this illustration of the two sorting algorithms, we're looking at the first and the third column. And we're going to begin with what we'll talk about the worst case, which if an array is unsorted, it's reversed. We're looking at columns 1 and columns 2. And what we'd expect is that both these would execute in the same time because they're n squared. They're going to have to go through all passes. So for example, think there's 40 elements in this data set, 40 outer, 40 inner passes, 1600 operations to complete this. Looking at it at the minute, you'd think that the insertion sort is going to finish quickly, but remember it has to got to its inner loop 2 to do all the swap operations, and bubble should eventually catch up and we'll see these complete at the same time. There's no noticeable difference when it is a worst case scenario. However, if we look at a nearly sorted data set, we should see that the insertion sort is more efficient. There will be less swaps, and we can use a flag variable to exit the insertion sort. If you have went through an inner pass and there has been no swaps, we know that the array has been sorted and we can exit it. So you don't have to continue on to all the outer passes because we can break out of it. And we should see in a nearly sorted array that the insertion sort wins. And there we go. The bubble sort is behind. It's eventually finished. So that's the efficiency of the two algorithms. They're both n squared, but you should be able to tell the examiner that if it's a nearly sorted array, you will recommend an insertion sort. And that's why it's often used in conjunction with other sorting algorithms. Right, so let's look at some of these excellent homework solutions. I'm going to look at, I think first of all, this is Christina's, and there's an interesting, which I can't figure out in Christina's, why it's throttling my machine, but we'll get to that in a minute. So we've got our bubble sort, we've got our insertion sort, classic, straightforward, well programmed, and then we've got the idea of racing these and timing them. And I'm going to run this and I'm going to choose the race. I'm just going to put in 10 elements, and Christina's algorithm generates an array with 12 random elements. So we've got the array, and then you can see, boom, it's throttling the computer. You know, to sort 10 elements, we'd expect this to be quick. And we wait with bated breath. And we're still waiting. There we go, and the results have come up on screen, and you can see that the insertion sort was 5 seconds, the bubble sort was 17 seconds, and obviously the winner. Now, that algorithm works, and it's programmatically it's sound. Obviously, just operationally, there's something going on here in the background, and can't figure it out if it's passing this array into another function and passing it on the fly, or if it's the use of the time library that's slowing this down. There's something, it's not the sorts, the algorithms are perfect, there's something in here that's sorting it out. However, it meets all the marking criteria and it's an excellent script. I'll upload that. Next we will look at, I think I might have Orange on screen, and again I like this because I'm going to throttle it with, I've slightly changed this. Orange script started with making an array by default of, how many elements? Make array. We will start with 1,000 elements in it. And I'm going to do my sorting race, 3. There we go, boom, very quickly it works, and we can see that the insertion sort was slightly faster. And again, we can't really take much into these because we don't know how sorted that array was, etc. I'm going to change this to working on a set of 10,000. So I'll stop that, change that to 10,000 in orange script, and I'm going to run it and choose an option 3, and we'll come back to that later, and we'll go and look at a final solution, which is Matus. And again, I'll upload these to the team. And again, excellent use of tkinter's Canvas widget to demonstrate these algorithms. We've got the algorithms, bubble and insertion, outer and inner loops, but then we've got an algorithm here that's basically going to draw these on the canvas. So if we run the sorting race, I'm going to enter in, we'll do it for bubble first, and you can see it's sorted with an excellent illustration, the insertion, and if we race them, I'll probably up that to see if there's any difference. We look at 20. And the insertion sort won that. Again, excellent illustration. We don't know the data set, so it would be unfair to draw comparisons in that. But all you're trying to do is improve your programming and understanding the mechanics of both these searching algorithms, which it's clear to me that you have grasped. So we'll finish by going back to orange, and it's still hanging there. You know, again, why is this? I would imagine it's Oren's algorithm for making the array, or if there's a print statement somewhere in here and not the actual sorting of it. So that's the sorting algorithms over, folks, and we meet again next Monday as usual to continue with algorithms and programming. Have a good weekend. Chat later.